Welcome to this presentation. We'll be looking at space trusses or 3D trusses and how we can verify our results of our analysis. Again, we're going to focus most of our analysis here on ANSYS or in ANSYS for two examples. I'll do one example in this presentation and another example in the next one. And so what we need to do with 3D trusses, like we did with our 2D trusses, is we need to shift from our element or body fixed frame of reference, our local reference, and expand that, or from our local coordinate system, to our global coordinate system. So from local to global coordinate system. And the way we can do that is with looking at these angles and finding overall cosine theta x. So figuring out how we can get this cosine angle here. And figuring it out from the 2x components divided by L. And we can do the same thing with the cosine of theta y and the cosine of theta z. Get those displacements as well. All this information feeds into determining how we can get our global coordinate form of our local coordinate form version of our stiffness matrix. So again, we're using these transformation matrices, but not the same ones we had in 2D. We have to use the 3D matrices, and that's what this guy is. So this is our big old 3D transformation matrix, but this is again the global coordinate form of our stiffness matrix. Right, so that's what that looks like generically for any positioned member in space. Because we need not just one theta, we need three different thetas to find how it's located in space. All right, so if you're doing this by hand, you would use this matrices, but again, I just want to give you that information. Pretty much all the rest of the steps are the same. All right, so let's focus on the verification of results for a bit here. One of the things we can do to verify our results is we can check our reaction forces. So in this case, we have the triangle, similar setup to example we've looked at before. But if we're fixed here at node A and at B we had a rolling joint, so we're just no motion in the y direction. If we will look just at the forces, the sum of the forces in the x direction, all we have is the 100 pounds, and then we have this reaction force at node A. And we can quickly find that's equal to the reaction force at node A in the x direction is negative 100 pounds. Do the sum of the forces in the y direction, we'd have a function of A and B, y components at A and B. And so that we wouldn't have enough information to solve, but if we also use the moments, some of the moments about node A, we could then find what B is and use that ultimately to back solve what A is. All right, so that's one way we can do quickly some hand calcs and evaluate those against what we actually come up with in our analysis. The next form or way we can verify our results is look at the sum of the forces at each node, which should be 0. So here's node 2 in the bottom right hand corner of our triangle. So we have this reaction force of 86.6 pounds, and so if we look at our two forces, they should work out to cancel that out. So again, sum of the forces in the x direction, we get the force in the negative x direction, so negative force 1 within element 1, and we also have the direction of the x component in element 2 going in the negative direction, so we have force 2 cosine 60 equals 0. And then look at some of the forces in the y direction, and don't have any components for element 1, but we do in element 2, so we can ultimately solve for the force in element 2 and making sure that's what it should be. All right, another option we have for verifying the results is number 3, pass an arbitrary section through the truss and analyze that. All right, so we got the 100 pounds at the top here. We draw an FBD. We got the 100 pounds. We got the force in element 3 and force in element 2. To the sum of forces in the x, and we can include the sine components of our two forces, some of the forces in the y, and we just have the y components of our two forces from the cosine of those. And if we need to, we could use the sum of the moments about a node to solve for that, but we have two equations, two unknowns. With this case, that would be done. All right, so 3 different ways that we can verify results, which is always good because if we didn't have the right setup for our ANSYS or any type of analysis, we want to make sure that we can look at our overall results and get a sense if we're on the right path or not. All right. So let's look at this example now. How do we do 3D trusses in ANSYS? So here's a setup. We got aluminum members, and we got, let's see here, node 1, 2, 3, and 4 up top here. And then we'll number these elements accordingly when we get into ANSYS, or at least how we're made, connected between our different nodes. But again, it's aluminum, cross-sectional area is constant for all of 1.56, and we have a modulus of 10.6 times 10 to the 6 psi. All right, and looks like our coordinates are given in feet, so make sure we keep that in mind as we put in the values there. All right, so let's go into ANSYS APDL. I assume you know how to start that by now. Go ahead and start with a title here. So change title, and we'll go Truss 3D. And go in here to preference and update that to structural. And click OK, because that's what we'll be looking at exclusively here. All right, so then let's go into the preprocessor and get that going here. Go element type, add a delete, add, and we're doing the link still. And just the 180 is nice kind of heavy hitter for everything in this arena here for looking at trusses. So go ahead and OK, close. Move on to real constants, add a delete, and add that, OK. And the area from our picture was 1.56 inches squared. So we're defining inches squared as one of our units, or inches as one of our units. So keeping that in mind as we move forward. Click OK and close there. Go down to material properties and material models, structural, linear, elastic, isotropic. And for the modulus, it was 10.6 e to the 6. And again, Poisson's ratio, go with 0.3 and click OK. And go ahead and close that. All right, so save DB. So let's go on and put in our nodes. So we'll go down here to modeling. And we're going to do a little bit different this time. Last time we created that grid and put things in. Now we have actual coordinates for each of our nodes. So we're going to actually plug in those coordinates directly. So go ahead and click on Create Nodes. And instead of on working plane, we're not going to have that defined. We're going to do an active CS. All right, so an inactive coordinate system is where we're defining it. And so this is great because you got a little bit more control knowing what's going on here. So we're going to define node number 1 to start. And again, we'll just go back to the presentation briefly to see what that is. So node 1 we have down here. And the coordinates are 0, 0, 3 feet. Right? And we'll go, instead of feet, we'll go inches. So going back here, actually this isn't great because you can see right underneath here. I've got 0 inches, 0 inches, and 3 feet. But we're in inches, so it's 36 inches. So don't hit OK. You want to hit apply, because what apply does allow us to put in another node coordinate, another node's coordinates, and if we hit OK, we just go back to the basic screen. So apply kind of keeps us in the same direction. So we'll change our node number to node 2, and we'll shift to node 2. So node 2 is 6 feet. Yep, 6 feet, 0, 0. So 6 feet is not 6 inches. We need to get that in inches, so that's 72. So 72 inches, and then 0, 0 for the other two. Oop, and we need to change the 36 to 0. All right, I'm going to click on apply there for node 2, and I'm going to go to node 3. So node 3, we're up here, so we got 0, 0, negative 3. So down here we'll do 0, 0, negative 3, so negative 36. Apply, and then node 4, we got 0, 6, 0. So 0, 72 inches for 6 feet, and 0. And now we can click OK because that's the last one we're defining. So let's go back to our ANSYS. All right, so that all should look good. Let's make sure we can see our numbers here. So we can see some of them there, so that's good. We can't see them all because we're looking again on a 2D plane. But let's get our numbering going so that we'll see our numbers at all times. So we'll keep that on, and we'll put on our element numbers as well, even though we haven't defined any yet. All right, we can again check our nodes, make sure we put them in the right place, so we can go list our nodes, coordinates only, and click OK there. We can see all the coordinates that we put in, so that all looks good. All right, so let's go ahead and save that. All right, now we want to see all the nodes to define the elements. So we need to change the position of what we have showing. So let's go to control plots and pan zoom rotate. And so going in here, we can go, we have ISO view or oblique view right here. We also have it here on the side. So let's do that because it's probably going to be more convenient. So right here on the side, we have isometric view, oblique view. So just click on that and you can just, you can toggle between them, see what they look like, see what you like best. So now I can see node 1, 2, 3, and 4. Right, so those all look good. All right, so let's go define our elements now. So we're going to create our, not nodes, but elements. So click here on elements. And we'll do, again, auto-numbered, and we'll do those through nodes. So same as time before. So we got our picker window comes up here. All right. So we didn't have any specific element numbering on our figure, so we'll just go ahead and go through here. So we'll just go 1 to 2, middle click, and then 1 to 3, middle click, 1 to 4, middle click, all right, 2 to 3, middle click, 2 to 4, middle click, and then 3. Now this is tough because you see it's kind of over top of same one, middle click. All right, but you can see element number 6 there. And maybe we can go back to oblique view versus isometric view, and we'll click OK on those guys. So what you notice there is they disappeared, right? We want to make sure we can see those. So let's go back to plot controls, and we'll go to numbering and element numbers, colors and numbers, and we'll apply and OK. Still don't see those. All right, so let's go back in here. And we want to make sure we can view these guys. Oh, yeah, plot. That's right. So we now plot elements. And it comes right back. All right, so instead of plot controls, go over here to plot and elements, and we can see them all show up there. So let's go and we change views now. Yep, now they stay on the whole time. All right. So again, that was under plot and elements. All right, so we look good there. Again, save DB if I haven't already. Let's apply our boundary conditions here. So we'll go into our solution and define loads and apply structural displacements on nodes. All right, so we're going to fix some spots here. So let's go back to our figure, see what we need to fix here. So we got displacement X, Y, and Z are fixed at node 1. X and Y are fixed at node 4, and just X is fixed at node 3. So X, X, and X are all fixed at those 3 nodes. So we'll start with that one, and then we'll work to the other 2. So let's click 1, 3, and 4, and we'll click OK. And we'll do all degrees of freedom. Oops, I'm sorry. Just X is 0 for those 3. All right, so that's 0. And click OK. And then we had Y is 0 at 4 and 1. So we'll click on 4 and 1 and get those applied there. So we'll go 4 and 1. And OK. And we'll make those be both 0. And then we'll come back in again and we'll say focus on just 1. And Z there is 0. All right, and then maybe we want to change view again to make sure we can see everything. All right, and how they're applied. And even here, it's kind of tough. So sometimes what you want to do is come and list loads and degree of free constraints on all nodes, so we can see that X, Y, and Z all for node 1 are 0. Just X on node 3, and then X and Y on node 4. So those look good. All right, so again, that was under the list menu and loads toward the bottom. All right, so now let's apply our forces. So we got everything's fixed there, so let's go on the forces. And let's go back, double check what we got here. So we just got 200 pounds straight down at 2, and that's about it. So the 200 pounds there. All right, so we'll do force on node. Pick our node 2, click OK. and we're going in the negative y direction, so negative 200, constant value there at y. All right, so we'll click OK. Looks good, and save DB. And let's solve this thing. All right, we got boundary conditions applied. We got forces applied. We have all the nodes and elements defined, so we should be good to go. So come up here to solution and solve. So solve current LS. Click OK. Solution's done. Close. Looks good. All right, so we can go through our process of looking at different things. I always like to look at the plot. It's always kind of fun, right? The deformed shape versus the undeformed shape. Click OK. Not seeing a whole lot. Let's see if we can look at. So there's kind of the. It says the left view, but it kind of looks like from the front, depending on what your perspective is. But you can see how it goes down, and it looks like a little bit to the right. All right, and kind of the top view there. There we go. There's the side view. So there you can see how it goes down there, deflecting. All right. So let's get some actual values here. So we'll list results and look at the nodal solution. Degree of freedom solutions, displacement vector sum. Click OK so we can see how it deflects. No deflection at 1 because we fixed that. 4 we actually see no deflection, though everything wasn't fixed there. Only X and Y were fixed, so it had no deflection to Z. And 3 was fixed there, so we can see some other displacements. Again, units are not shown here, so you need to make sure you add that on your own if you're letting somebody know about this, and these are all in inches, because that's what we used and defined things as. All right, so if we want to look at what's happening in the elements, we have to go to our element table. So come back out here to element table. You need to define what's going on, so we can add. Same process as force, so we'll look at axial force. Slide down, get SMISC 1 for force. Come back here and go axial stress. And slide down and we'll go with LS again, LS1. And click OK for that. Closing that, and we can list our element table, selecting our force and our stress. And click OK. And we get our forces and our stresses. Again, units not shown, so make sure you know what's going on here. We got forces in pounds and stresses in pounds per square inch. Right. And last thing, if we want to look at the reaction forces, like we've done before, let's go back, list results and reaction solution, and go ahead with all items so we can see the reaction forces there. All right. 100 pounds at node 1 in the X direction, 100 pounds at 3, node 3, and negative 200 pounds and 200 pounds at node 4 there. All right, so I hope you enjoyed the video. Let me know any comments in the section below, and then check out the notes for if you want to jump to anything in the future if you've already seen most of this. All right, I'll see you in the next video.